Hi guys, I hope you're all doing well today. Before I get started, I just want to remind you that on the class page I have put the Best Lent Ever series there if anybody's interested in continuing to watch those little video clips each day throughout Lent, since we are not in the classroom to do it together. If you haven't noticed it's there, it is there under class resources, so you can take advantage of that if you would like. So today's lesson is going to describe how calorimeters work and how they're used to measure heat flow. You might want to reference section 17.2 in your text and maybe have a calculator handy because we are going to be doing some math today. So calorimetry is just the science of measuring heat, and in order for us to make accurate measurements of heat being given off or heat being absorbed during a chemical or physical change, we use something called a calorimeter. So a calorimeter is that device that we would use. And I have a picture of the calorimeter on this slide, and you can see it looks like a styrofoam cup if you look at it closely. And basically we use this styrofoam cup because the styrofoam cup it insulates the reaction that's happening inside. You can also notice that there's a lid or a cover on top of that styrofoam cup, and in that, or going through that cover, is a thermometer that can measure the temperature change that's occurring when the reaction's happening, and also something to stir the contents inside. And you can see it's filled with liquid, and that liquid is usually water. And maybe whatever chemicals you're using, those would be in there as well. So that is just a little look at the calorimeter before we get into the math portion. So here's some key points that I want you to really kind of focus on when we're talking today. So in calorimetry, and I'm just going to read this. I hate reading slides, you know that, but this says these key points perfectly, and this is directly from your textbook. The heat released by the system is equal to the heat absorbed by its surroundings. And we could say the opposite. The heat absorbed by the system is equal to the heat released by its surroundings. And we talked about this in a previous video. When heat is released or heat is absorbed, it's equal. We're not losing any energy or heat when a reaction is taking place. So if heat is leaving a particular reaction and heating up water, per se, in the calorimeter, that heat exchange between the water and the system or the reaction is going to be equal. It's going to be the same magnitude, we could say, if we want to use maybe a more scientific term. So these are the key points that are going to come into play as we start talking about the math in this particular unit, or this particular section. So let's talk about these constant pressure calorimeters. Again, they're also known as coffee cup calorimeters because they are styrofoam cups, and we put coffee in styrofoam cups very often. Now, the reason it's called constant pressure is because normally we're working in a lab and our reactions are open to the atmosphere, and atmospheric pressure is always pretty constant, and so it's called a constant pressure calorimeter because that pressure is staying constant throughout the reaction. And because we are at constant pressure, we can say that the heat released or absorbed is equal to its enthalpy. So we can say that Q, or that heat released or absorbed, is equal to delta H, or that change in enthalpy. And we'll talk a little bit more about what that means when we start to get into the math. But we can make that statement that heat released or absorbed is equal to the change in enthalpy. So before I get started on specific heat problems and looking at their reaction or the equation that we're going to use, I want to remind you of the specific heat equation that we used yesterday. And that equation, we said C sub P, which stands for specific heat, and we looked at what that equals, and it equals Q, or heat, divided by mass times delta T. Now, specific heat problems, we're actually going to be looking at the heat, or calculating the heat of the reaction. So I could take this equation and I can rearrange it to solve for heat. So when I do that, what I'm going to do is multiply both sides by the mass times delta T, and so Q ends up by itself, and we have mass times delta T times C sub P. And you're going to see in a minute that that's the exact equation that we're going to be using to solve these specific heat problems. So Q equals M times delta T times C sub P. So here's that equation written out on this PowerPoint slide. Oh, which, by the way, all of these PowerPoints that I'm doing the voiceovers on, the actual PowerPoints are underneath the PowerPoint note folder in this section on the class page. So you can always access these or not the videos, but the actual PowerPoints without my voiceover in that folder. I'm not sure if anybody noticed that, and if I even mentioned it. Again, still trying to get used to this online teaching. So let's take a look at this equation. First, we know that Q is going to be looking at the heat absorbed or released in the reaction. That's what we're solving for. M is mass, usually in grams. I should say it is in grams, not usually. It always is in grams. C sub P is the specific heat. And I have in parentheses there appendix. Remember, I showed you that table in the last video from yesterday. There's a table in your textbook, and there's, I believe, also a table in the back of your textbook as well. So there's one embedded in the chapter and then one in the back of the textbook. So that's what that means. And again, that's something that you're going to get from the table. And usually our C sub P is going to be the specific heat of water because the reactions are taking place in water. Delta T is that temperature change, and if you remember, we talked about that temperature change before. Delta T, we're going to take the final temperature minus the initial temperature. And if we get a positive number, that means the final temperature was warmer than the initial temperature, and when we subtract, we get a positive delta T. And if our delta T is negative, that means the final temperature was lower than the initial temperature, and that means that the reaction cooled off. So if delta T is positive, that means warming or an exothermic reaction. If delta T is negative, that means cooling, and it could be endothermic. So let me just add that to this slide. So warming would be exo, and cooling would be endo, giving off, warming would be giving off the heat, cooling would be absorbing heat from the surroundings. So when we run a reaction, we have the mass of water that we're going to add to that coffee cup calorimeter. We know the specific heat of the water, and we can figure out a temperature change because we have that thermometer that is inserted through the lid of the calorimeter. So we have all of that information, and we can solve for Q. A couple things that I'm going to add on here, because we said that delta H equals Q when we're talking about constant pressure. We want to also be reminded that we have a system and we have its surroundings. So the system is the reaction that's actually happening, and the surroundings would be what's happening to the water. Is the water getting cooler in that system, or is the water getting warmer in that reaction? So we can say that Q of the system is equal to delta H. So I want to make that clarification. And because the amount of heat that is released or absorbed in the system is going to be equal and opposite in charge of the surroundings, I can say that negative Q of the surroundings equals delta H. And then we know that if we're solving this particular equation with the Q equals M C sub P delta T, we can say that mass times C sub P times delta T, oh, that's not going to show up very well, I apologize for that, is also equal to what we're saying. So the Q of the system equals the delta H. The Q of the system also equals the negative Q of the surrounding because they're equal and opposite in magnitude. And we're going to look at some examples mathematically of this. And we can also say that the Q of the system is equal to negative of the quantity of mass times C sub P times delta T. And I know that maybe that doesn't make sense right now because we haven't looked at any of the math, but this is going to be super important to remember when we do start looking at that math. Okay, here's our first problem that we're going to tackle. This one's actually a sample problem from your textbook, so if you have your textbook handy and you want to pause the video to open up your textbook and kind of follow along with the work, you most certainly can do that. It's on page 513 in your textbook, and it's sample problem 17.2. There's a lot of words here. So I'm going to read the problem, and I'm going to highlight the things that are important in this problem so that when we start to do the work and try to figure out what we already know, what we're trying to figure out, we have everything highlighted in the problem, and it'll make it kind of easier to solve then. So as we read through this problem, it says when 25 mils of water. Well, that seems important because remember, water is the surroundings, and we need to know how much water we have in those surroundings. So we have 25 mils of water that contains a certain molarity of hydrochloric acid. That's important, but the moles of the hydrochloric acid is not something that we really are going to take into consideration here. It's more the water. Even though we're adding a little bit of hydrochloric acid to that water, it's not going to change the composition of that water so much so that it's going to change the mass of that water. Okay, so the 25 mils of water is more important than the molarity of the hydrochloric acid. Okay, so I'm not going to highlight that. But you'll notice next it says at 25 degrees C, and that's important. We know we need to know the temperatures of the water before and after the reaction occurs. So that is important, so I am going to highlight that. So when 25 mils of water containing 0.025 moles of hydrochloric acid at 25 degrees C is added again to 25 mils of water containing 0.025 moles of sodium hydroxide, so we're adding a base. Again, molarity of that sodium hydroxide, not important. It's a very small amount, so it's not going to have a significant impact on the mass of the water. Also at 25 degrees C, we're going to put this in a foam calorimeter or coffee cup calorimeter, and the reaction is going to proceed. Now remember, in this coffee cup calorimeter, I have that thermometer that's sticking into the water to measure any temperature change. So what we need to do is calculate the enthalpy change. So enthalpy change in kilojoules, remember enthalpy is delta H, okay, not Q, delta H, during the reaction. The highest temperature that was observed is 32 degrees C. So there is part of our temperature change. We have an initial and now a final temperature. And something important to remember, since we're given the mass of water, I'm sorry, not the mass, the volume of water, we can use the density of 1.0 grams per mil to convert that right over to grams of water, because we need grams of water to solve this problem. So let's look at what we need, and let me draw a schematic of what's going on in this particular reaction. So we have our coffee cup calorimeter with the lid on top and a thermometer sticking in there. And also we could show the stir bar, or the stir rod, but I'm not going to show that. We've added 25 mils of water that has HCl. So I'm going to put 25 mils of HCl. And we've also added 25 mils of NaOH. That reaction is going to occur in the water, and we're going to notice that the temperature rises. So I have a temperature increase in the water. So my surroundings, the temperature increased. The reaction, or the system, the temperature decreased. Okay? Remember, equal and opposite in sign as well. So that is the reaction and how we're adding everything to that reaction vessel. So let me erase that, and let's talk about what we know and get that all written so that we can proceed with doing the math. So one thing I know is the volume, let me switch back to the pen, the volume of the water is 25 mils of the HCl plus 25 mils of the NaOH. So I have a total volume of 50 milliliters. Okay, so that's my total volume. I know that the density of water is 1.0 grams per mil. Sorry, I'm trying to write small so I can fit everything. So my mass of water is going to be 50 grams. Okay, so just using the density of water, I can get the mass. So now I know the mass of the water, my M in this case. The next thing that I want to look at is that delta T. So delta T, I started, my final temperature, TF minus TI, my final temperature was 32 degrees minus my starting temperature of 25 degrees. So I have a temperature change of 7 degrees C. Okay. What else do I know? Well, I know the C sub P of water, and this reaction is mostly water. Remember, I said the amount of hydrochloric acid and sodium hydroxide in this reaction is minimal. So it doesn't change the mass of the water, and it doesn't make the C sub P or the specific heat of the water any different. It's mostly water. So the C sub P of water is 4.184, and we said that is joules per gram degrees C. Okay? I think we have everything that we can solve for the problem. So we calculated the mass of the water. That was something that we did earlier. Now we're going to calculate delta H. Remember what I said, when we are talking about delta H, it's going to equal the negative of the negative of the mass times C sub P times delta T. So now we can plug in the mass, which was 50 grams of water, the 4.184, I'm going to run out of room, joules per gram degree C. I'm going to write the next thing down here, which is the delta T, which is 7.0 degrees C. You'll notice I have degrees C in the numerator here, denominator here, grams in the denominator here, numerator here. So I'm left with joules. That makes sense. So my delta H is going to be negative 1.5 times 10 to the third joules. That makes sense. Let's talk about why that makes sense. We had a temperature change where the surroundings increased, so the reaction gave off heat. If a reaction gives off heat, it is exothermic. What do we know about the sign? Forgot my equal sign there. What do we know about the sign of delta H when a reaction is exothermic? Well, we talked about that in a previous video. And if you remember, a negative delta H is an exothermic reaction. So it makes sense that our delta H is negative. Now, I believe that the problem asked you to answer this in kilojoules. So we can do a quick conversion. It's 1,000 joules in 1 kilojoule, and really all that happens here, I'll write this in a different color so it's easier to see, is my delta H. I get rid of that exponent, basically, because 10 to the third is 1,000, so delta H is negative 1.5 kilojoules. And you can do that conversion and just double check that work and make sure you get negative 1.5 if you had to convert it to kilojoules. Okay, so that is our first problem. And let me leave that up on the screen just for a second for you guys so you can take a look at it. You can also pause the video as well. Okay, so now we're going to move on to a different type of problem on the next slide. One thing I want to mention about the problem on the last slide, I kind of got ahead of myself on the slides here, but if we were calculating the heat released and not the delta H or the enthalpy change, the Q would actually be positive, because when we are talking about an exothermic reaction or heat being released, Q is actually going to be a positive 1.5 kilojoules. I just want to make that distinction. In this case, we were talking about calculating the delta H, or the enthalpy change, and using the negative mass times C sub P times delta T. That's going to either give us a positive or negative delta H, depending on whether it's exo or endothermic. But if we were to do Q, when heat is released in a reaction, Q is going to be positive. When heat is absorbed in a reaction, it's going to be negative. So I just want to make that distinction before we move on to this practice problem. Okay, so looking at this problem, again, what I want to do for you guys is I want to read through the problem. I want to highlight the things that are important, and then talk about what's going on in this practice problem. So in this one, it says a piece of metal. So now we're not dealing with liquids, we're dealing with a solid metal. And it has a mass of 59.047 grams. That's going to be important because we know we need the mass in our calculation. It was heated to 100 degrees C, and then it was put in 100 mils of water. We know 100 mils of water equals 100 grams of water because the density of water is 1. I showed you that math on the last slide. And the initial temperature of water is 23.7 degrees C. The metal and water are allowed to come to equilibrium. That means that either the metal is going to give off heat or the water is going to give more heat to the metal. Well, if we look at this and the metal's going in at 100 degrees C and my water is 23.7 degrees C, most likely that metal is going to be releasing heat to the water, and the temperature of the water is going to increase and the temperature of the metal is going to decrease in the same magnitude. So the metal and water are allowed to come to equilibrium, and the temperature is determined to be 27.8 degrees C. So that's our final temperature. We're also going to assume no heat loss to the environment, and I want you to calculate, in this case we're calculating specific heat of the metal. So let me draw a little schematic about what's happening here in this particular reaction. So I have my coffee cup calorimeter with a lid, thermometer goes in. I'm adding a hot piece of metal to this reaction vessel. That piece of metal is at 100 degrees C. The water is at, what did we say, 23.7 degrees C. And we want to calculate the temperature difference. How much is the water temperature going to increase when that metal starts releasing heat into the water or into the surroundings? Okay, so that's what's going on in this experiment. Now the next thing that I want to talk about is this Q of the system equals a negative Q of the surroundings. So we have two things going on in this reaction. We have a system, that's the hot metal, and we also have the Q of the surroundings that we have to take into account here. So we're going to be setting up two Q equations. one for the metal and one for the surroundings. So what we're going to have here is a mass times C sub P of the system. That's what we're solving for, and the delta T. And we're going to set that equal to negative mass C sub P of the water, because that's our surroundings, and the delta T of the water. So we have two things going on here. So let's kind of fill in the blanks. What do we know on each side of these equations, and then solve for what we don't know? We know the mass of the metal was 59.047 grams. We know that. We do not know the C sub P of the metal. That's what we're trying to figure out. And we know the delta T is going to be 27.8 minus 100, because this is TI, or TF minus TI. Sorry about that. Okay, so that's where I got those numbers. So that's one side of the equation. If I wanted to simplify, I could do that subtracting and put that number in there. So why don't I do that right now? When I subtract these two numbers, I'll just erase that. TF minus TI in case of the metal is going to be negative 72.2 degrees C. Okay, so that's one side of the equation. The next side of the equation, I'm going to talk about the water. So the mass of the water here, it was a volume of 100 mils. We know that that's 100 grams. I mentioned that before because the density is 1.0 grams per milliliter. The C sub P of water we know is 4.184 joules per gram degree C. And again, I'm going to run out of room, so I'm just going to write the second part down here. And we're going to multiply by the delta T. In this case, the delta T, we're going to take 27.8 minus 23.7, final minus initial, and we get a temperature change of 4.1 degrees C. I have everything but the, I could say kitchen sink here, but I'm going to say specific heat of the metal, and specific heat of the metal is what we're solving for. So I'm not going to show you all of the work here, but what I would do on the left-hand side of the equation is I would multiply the 59 and the 72.2. I would multiply those two things together. I'm going to get a negative value there, and then I would multiply everything on this side together, and I would solve for C sub P by dividing the product on the left by the information on the right. So since I'm running short on screen here, I'm just going to give you the answer, and I want you to try to do the work. If you are having trouble trying to figure out that answer, please go into the forum and ask me a question, and I can show you all of the steps that I did. Since we're talking about C sub P, when I look at my units, they should all cancel, and then I should end up with a joules per gram degree C, and 0.402 would be the specific heat of this metal. Okay, but this is, again, that's algebra to solve for C sub P. So give yourself a chance to try that and see if you come up with that answer of 0.402 joules per gram degree C. Now there's one minor little thing, no math, that I want to talk about as far as calorimeters. And the last thing that I want to talk about is one other type of calorimeter. Again, we're not going to look at the math involved in this type of calorimeter. I just want you to be aware that we have two types of calorimeters. We're focusing more on the constant pressure because it's the one that if you were working in a lab, you would be using in a school lab. You might come across the constant volume calorimeter in college or out in the workforce, but we're not going to do any math with this one. I'll leave that up to your college professors. So this is also known as a bomb calorimeter, because what you actually do in this one is you have a chamber on the interior of this water-filled bath, and you put your sample in that chamber, and you burn it. So you're setting it on fire at very high pressure. So we have pressure changes here. The pressure in this system is not going to be constant. It's not going to be atmospheric pressure. You're increasing that pressure. And then heat is going to be released because you're setting something on fire, burning something, and it's going to change the temperature of the water. So on the outside of this area, you have water surrounding. And again, you have this thermometer that's going to take the temperature change. And when you measure that temperature change, you can calculate the heat that is released, or that Q value, or even the enthalpy as well. So that's a bomb calorimeter, or constant volume calorimeter. And again, not something that we're going to do any math with, but just something that I want you to be aware of. So let's take a look at what your assignment is going to be. I did upload a calorimetry worksheet to the worksheet folder that you can find on the class page, and I would like you to complete that worksheet. I think there's 5 problems on it. If you want to, on that same worksheet, do the textbook problems that are assigned, you can do that as well, or you can do 2 separate papers and you can submit them to the Dropbox. The textbook problems can be done, again, on the worksheet. You can submit them together or you can submit them separately. And photos are acceptable. I just want to make sure that your work is handwritten when you submit that photo. Okay, this isn't something I'm grading. I'm just looking at it for completeness. All assignments from this point forward are going to be due on the Friday of the week that they're assigned. So today's assignment won't be due until next Friday at midnight. So it gives you a week to kind of use your time management skills and figure out how you want to get the work done. So I won't be looking and checking for any homework until the Friday of the week, and that's how it's going to work for the remainder of the time that we're doing online schooling. Okay, just so you know, on Monday we'll be able to start 4th quarter grades, and this will be counting as part of those 4th quarter grades, but again, not due until next Friday, April 3rd. Okay. Anytime I'm grading something, I will let you know that I'm grading it, and that you can submit that to the Dropbox, and that would have to be not a photo, it has to be a PDF, and I will let you know when it has to be done that way. Okay. Again, I apologize for the length of this video. There was some math there that I wanted to make sure that you understood. And again, take some time to do the work, and if you have questions, please ask in the forum. Set up a new topic, and I will be sure to answer. Or if you feel more comfortable emailing me, you may email as well. I am checking both the forum and the email throughout the day. Okay. I hope everyone's doing great. I know it's hard to be home, but try to stay positive. At least you get to hear my voice. I don't know if that's good or bad, but stay safe, stay positive, and I'll catch you in the next lesson.